In this fourth and final video, we review what we've seen in the previous ones, make some conclusions, and then look at some further real numbers and some interesting properties. So as we've seen, many mathematical problems concerning real numbers are easy to understand but remain unsolved. They remain as conjectures, thought to be true but not yet proven. One either has to prove or disprove a statement. So you will recall in questions 10 and 11, we looked at the sum, pi plus e, and the product, pi times e, of two well-known transcendental and irrational numbers. And we asked the question whether these were transcendental or not. And what we learnt was that whilst it is known that at least one of these is transcendental, and hence so irrational, it is not known which one. So we begin by proving that at least one of the sum and product of those two transcendental numbers is irrational. Let us recall that solutions of polynomial equations with rational coefficients are algebraic, either rational or irrational, and so are not transcendental. Because pi and e are transcendental, they are not solutions of a polynomial equation with rational coefficients. So let's suppose the opposite, that pi plus e and pi times e were both irrational. Then the polynomial quadratic equation, as shown, would have rational coefficients. On the other hand, that quadratic equation can be rewritten in the form shown, whose solutions are pi and e. That would mean that pi and e would be solutions of a polynomial equation with rational coefficients. And that's clearly a contradiction because pi and e were transcendental, and thus pi plus e and pi times e cannot both be rational, i.e. at least one of these is irrational, but we don't know which one. We now follow a similar argument to show that at least one of the product and the sum is transcendental. So while we know that solutions of polynomial equations with rational coefficients are algebraic, and that because pi and e are irrational, they're not the solutions of polynomial equations with rational coefficients, one can say the same for polynomial equations with algebraic coefficients. So solutions of polynomial equations with algebraic coefficients are algebraic, rational or irrational, and so not transcendental. But because pi and e are transcendental, they are also not solutions of a polynomial equation with algebraic coefficients. So let's suppose the opposite, that pi plus e and pi times e are both algebraic, i.e. not transcendental. That means they're the solution of the quadratic equation shown, which would have algebraic coefficients. On the other hand, if we rewrite that quadratic equation as shown, whose solutions are clearly pi and e, we see that pi and e would be the solutions of a polynomial equation with algebraic coefficients. And that again is a contradiction, and thus pi plus e and pi times e cannot both be algebraic, i.e. at least one of these is transcendental, i.e. at least one is irrational, but we don't know which one. So pi and e have the property that they are transcendental, and their sum and product are thought to be transcendental and therefore irrational, but this remains a conjecture. In questions 8 and 9, we looked at the powers shown, asked whether these were transcendental or not, and we said that it is not known that these are irrational or rational, let alone whether they are transcendental or not. one can also consider the power pi to the power pi. Again, ask the question whether it is transcendental or not, and unfortunately the same conclusion, that it's not known if it's irrational, let alone whether it is transcendental or not. Now you might recall that we didn't look at question 12, which concerned the power of e to the pi. And we asked whether it was transcendental or not, but we didn't give an answer. Now, in order to do that, we need to consider numbers beyond the reals. Are there any? Well, the quadratic equation shown clearly does not have real solutions. There's no real number, x, whose square plus 1 is equal to 0. And so solutions of that equation are clearly not real, but they are algebraic, because they would be solutions of a polynomial equation with rational coefficients, which that one has. The coefficients are 1 and 1. So we need to classify a new set of numbers which are non-real numbers, and these are called complex numbers. They're of the form a plus bi, where a and b are real, and I satisfies that quadratic equation, i.e. I squared plus 1 is equal to 0. This includes all real numbers, because when b is equal to 0, the complex number is just real, it's the number a. It also includes what are called purely imaginary numbers, where a is equal to 0 and b is not equal to 0. Are there yet more numbers beyond the complex numbers? If so, are they algebraic or transcendental? Are there yet more mathematical structures beyond that? So let's return to e to the pi. This is its approximate value. And in order to decide whether it is transcendental or not, one needs to use the theorem that we stated in the first video, proved in 1934, which is that if you raise an algebraic number to the power of an irrational and algebraic number, it will be transcendental, provided the algebraic base is neither 0 nor 1. Now we know that e is transcendental, so it's not algebraic, and it's also irrational. We know that pi is irrational and also transcendental, so it's also not algebraic. So we have e to the pi being a transcendental number raised to the power of an irrational and not algebraic number, which sadly means that that theorem is of no value as yet. In order to make it of value, to look at e to the pi, consider Euler's identity. As shown, -1 equal e to the I pi, where I squared is -1, or I is equal to the square root of -1. This is arguably the most famous expression in mathematics. It contains the natural number 1, the two most well-known transcendental and irrational numbers e and pi, and the imaginary unit I. If we raise both sides of that expression to the power -i and simplify, as shown, using the normal rules of powers, which are valid here, and the fact that I squared is -1, we see that e to the pi can be written as -1 to the power -i. Now the base -1 is algebraic. The power is also irrational and algebraic. That gives us scope for using the theorem. So -1, the base, is algebraic because it's the solution of x plus 1 equal 0, a polynomial equation with irrational coefficients. The power, -I, is also irrational and algebraic. It's irrational because it's not even a real number. It's not of the form p divided by q, where p and q are integers and q non-zero. It's also algebraic because it's the solution of x squared plus 1 equal 0. Check that. With rational coefficients 1 and 1. So returning to the famous Gelfond-Schneider theorem of 1934, which says that an algebraic number raised to the power of an irrational and algebraic number must be transcendental, where the algebraic base cannot be 0 or 1. We already have that -1 is algebraic and I is irrational and algebraic. We have that e to the pi is equal to -1 to the -I, which is an algebraic number raised to the power of an irrational and algebraic number. And hence, by the theorem, e to the pi is indeed transcendental, and hence irrational, shown due to that theorem back in 1934. So of the four possible powers of e to the pi, pi to the e to the e, and pi to the pi, the only one for which is known that it's transcendental is e to the pi from the theorem. And so almost finally, one can extend that result to consider similar powers e to the pi times the square root of n, where n's a natural number. That's also transcendental, shown some while later. We know that pi and e to the pi are now both transcendental. What about their sum? Is that transcendental? What about their difference, e to the pi minus pi? Well, we know the value of pi and the value of e approximately. So if we work out e to the pi, as we've already seen, it's approximately 23.14069. And what you notice is that's close to 20 plus pi. Indeed, e to the pi minus pi is equal to 20 to within 0.0045%. A very good approximation. But of course that hasn't answered the question we've asked, either about e to the pi plus pi or e to the pi minus pi. And finally, coming back to our e to the pi, which is definitely transcendental, and pi to the e, which we don't know, what about their difference? Well, it's the difference of a transcendental number and one which we know to be either algebraic, so rational or irrational, or transcendental, but we don't know which of any of those categories pi to the e fits into. So all of these are still possibilities for that difference. We can also ask the question about which is the bigger of those two numbers. And in fact, one can easily calculate that e to the pi is bigger than pi to the e. But can you prove it without doing the calculation mathematically? Could you, for example, use A-level calculus to show that? Well, yes, you can. Why don't you try it? Oh, and by way of a hint, you might like to consider the function x to the power 1 over x. Good luck. and thank you for your attention.